Good. Okay, so welcome everyone for our RAISE Center of Excellence training today that we have on graph neural networks. So we have a couple of speakers today that will provide you with, let's say, a short introduction around graph neural networks, and then also some insights about how you can use these interesting new technology with numerical simulations that will be provided by Nicoletti from AutoEncoders. And then afterwards, we have also an insight from CERN. So basically using then the same technology for a complete different application field that is basically this particle flow reconstruction that they have at the Large Hadron Collider down there in Geneva. I give my best to stay in time with all the presentations, that there will be a Q&A session at the end. So hence, we will push a little bit the questions to at the end to enable a better discussions on them and to stay in time in this basically recording that we do as well for YouTube here. But of course, if you have questions already, please put them in the chat and we will reiterate on them when we come to the Q&A session later. So for those of you who not really know something about RAISE, we will also give a very short introduction about this. But firstly, we want to hear a little bit what are the speakers. So as I said, firstly, it will be a little bit introduction maybe from myself, but then we have the major part of this particular seminar today from AutoEncoders, and Nicoletti is really an insider, senior data scientist that can show you a little bit how basically AutoEncoders is doing. Of course, he could talk for hours how you can combine machine learning with really basically simulation sciences, as we would call this, so numerical simulations based on known physical laws, and how you do this with high performance computing and how this actually also scales to exascale in the future. And after that, there will be Eric Wulff. He is also a very experienced AI software engineer in RAISE, basically works at CERN, so at the Large Hadron Collider, as already mentioned, and is in the division of the CERN Open Lab there, and really also nicely combines the field of physical sciences with AI and machine learning technologies today. Shortly from my side, I'm basically full professor here at the University of Iceland since a couple of years, teaching high performance computing and parallel and scalable machine learning. And I'm also 18 years now in the Wulff Supercomputing Center in Germany. And for the project itself, might be relevant that I'm also in the joint undertaking, basically one of the governing board members of Iceland here. And the idea is really of the Center of Excellence is to continue all of those. They're not only the RAISE project available for you to learn essentially from all the different sciences and technologies in HPC, but there's really a wide variety of Center of Excellences, and they are basically also planned to exist for a long time in the European space. So this whole is organized basically as a RAISE project, but also in combination with the EuroCC National Competence Center for AI and HPC in Iceland, this NCC Iceland here. That's why I shortly talk about a little bit about this slide. We have around 3,000 students at the School of Engineering and Natural Sciences, and around, I would say, 500 master students and doctoral students. And definitively many Erasmus students. So half of my course is usually from Germany, from US, from France, from different countries in Europe. And you see here, we follow in the simulation sciences and AI, a strategy of so-called simulation and data labs in close collaboration, actually with the Wulff Supercomputing Center in Germany, where we have basically joint members in all of these different labs, reaching from neuroscience up to remote sensing, acoustics as a very specific lab, or health and medicine. So with this combined, we in the EuroHPC ecosystem strive towards exascale and basically as a forefront of Europe. You see here not only our collaboration partner Wulff, that with any luck very soon will have in 2023 or 2024 maybe an exascale system. And we are already on the path with Iceland, for instance, also contributing to the LUMI system, basically, which is both driving in one way or another a modular supercomputing architecture that I would encourage you to look at. If you want a little bit here, you see in YouTube a video on that. So this is on the strategic way towards, let's say, the idea how we can enable exaflops essentially in Europe. So, and I think that's all I leave on the table here for you from the organizational perspective. Now let's move a little bit into the RAISE project. Why is a kind of webinar on graph neural networks now relevant for RAISE? So in order to show the relevance then of this interesting graph neural network technologies, it's maybe good to know a little bit about the CoE RAISE project. As I said, it's one of the Center of Excellences in Europe in the area of HPC, but then very much focused on different application areas. And the one of CoE RAISE is definitively based on engineering disciplines with AI as one of the mainstreams, but of course not losing sight of the as I said earlier, the numerical simulations based on known physical laws. If you want to know more about the whole project, I could talk here for 2 or 3 hours. That's not what I want to do. Rather keep it rather quick. We have a very good website. In the RAISE website, you see definitively many of our use cases, our news articles where we are in the RAISE project. So I provide you here really with some of the fundamental ideas what the CoE RAISE really entails, and why all these buzzwords, big data, AI technology, exascale, simulations, kind of all matter for this particular project. So you see here one of the driving ideas and the motivation perhaps here a bit of this RAISE project, that we had many simulations here in the past that use HPC a lot and also are able quickly to scale very high. We see a computational fluid dynamics code, which is also the capability to really take advantage of HPC a lot, and obviously also generate a lot of data, which enables us also to learn essentially from all of these different simulations with AI technologies like deep learning you probably already heard. So one of the elements, however, with AI technologies is that this is a community not directly moving to exascale. So there we have a community that mostly works with workstations under the desk with GPUs, perhaps not scaling up to very many. So hence, in the last couple of years, there's a momentum of really driving these AI technologies to the scale as well. You have probably heard that HPC systems by now with V100 or A100 cards from NVIDIA, and soon perhaps also with AMD cards, have now lots of equipment to also enable AI technology at scale. But this is not so obvious. So the software technologies that enable us to do this is basically one of the matter of research to really understood and enable for scaling within the CoE RAISE project. And by doing so, we have, of course, many benefits, not only for the AI itself to learn from large quantities of data, but also to enable then training of, for instance, surrogate modeling and surrogate models, which then could enable us to really replace certain very cost-intensive simulations that burn otherwise many cycles, where with inference in AI, you here and there have much better, let's say, leverage of resources that then are not so costly, or they could additionally inform the simulation with some, let's say, AI generated models. Obviously, that is very abstract right now. Hence, in the CoE RAISE project, we really have a couple of very clear use cases. You see here 5 different compute-driven use cases where really physics is a major driver of all of these use cases. And on the other hand, we have more data-driven use cases where the large quantities of data that we get, perhaps, for instance, that you will hear today from Eric with the fundamental physics in CERN, but also from remote sensing data sets from Earth science satellites, Earth observation satellites, and up to 3D printing, manufacturing. So also many of those have really big data to offer to learn at scale from AI. So, and this shapes a little bit the CoE RAISE project. So we're talking about the so-called application co-design of a software framework where we have already the first blueprint. But the first takeaway message for the seminar today, when we talk about AI models like the graph neural networks today, is really that all of these create, let's say, lots of data sets that needs to be processed. No matter it's the data intensive ones. Also, if you look at CFD simulations, in different areas of sciences, you see also wind farm simulations can be very data intensive. And so learning from them is, of course, an interesting part. And not all of them are just simple images, or let's say what we know also from other areas like text or videos, image capturing or translation of languages. Here we talk about very sometimes unstructured data where it's not at all clear how you actually use that with a typical, let's say, neural network that you maybe know already from. I've heard that there was big impact in computer vision from so-called convolutional neural networks, I'm sure. But here we talk about sometimes really data sets which don't really fit one-to-one to this, let's say, rather simple scenario. And we will learn more about this when I introduce a little bit the graph neural networks, but then also looking into the use cases that we had at CERN on the one hand, and then also from Atos in basically in all the different numerical simulations. But of course, it is a prerequisite to have the data available. Now, what we do with this is basically we have work package 2, so to speak, that is bridging between these two use cases, really trying to help to understand and benchmark and scaling up these technologies. There are different frameworks that help up in scaling, like Horovod, DeepSpeed, PyTorch, DDG, lots of technologies that really needs to be analyzed of how much they actually scale. A couple of GPUs usually is not a problem, but probably some of you have heard when you really scale very high with GPUs, you have a problem of batch sizes that suddenly really decreases the accuracy significantly. So we study these phenomena, but also, of course, technologies like that want to scale very high need a hell of a lot of data. So here we're thinking about what data augmentation approaches we can do. So is there something like we can do what you probably heard already from Google, pixel in, pixel out in images, something like this, maybe also for the simulation sciences. So in the end, it is a loop, if you want to really understand it with the AI technologies and then with the simulations we had and the data to see what of these technologies get, so to speak, from us a stamp of being approved to actually scale towards exascale, which is not at all clear. And we're talking here really 10 to the 18 performance, which is quite something for the AI technologies at least. Now, one specific approach that we also have in the project is, of course, the hyperparameter tuning, where lots of benefits are automatically given by the HPC systems, where you try to find the neural network architecture maybe in a more or less semi-automatic way. You tune the architecture based on all the different hyperparameters, because all of those are also not at all clear how you actually pick and choose them. So here HPC and especially then exascale has lots to offer, because there you basically have no limits of really finding perhaps the best architecture, or almost the best, I should say, for a given problem at hand. That's also something that we study. And if you look a little bit how we basically see this today combined then with the hardware and the software architecture, you see here a little bit this idea on the left-hand side, because all of them play a little bit into the perspective of how users really would use all of this combined. The data-driven use cases and computer-driven use cases really require software that scales. But of course, as we will hear today also, the hardware infrastructure underneath will be also a very important factor. So there's also something we focus on and which is constantly moving in the field of high performance computing. While the accelerators were rather new 10 years ago, and with NVIDIA, we gained some market share in this direction, we see suddenly AMD arising with a complete different framework, not anymore cuDNN, CUDA, Nickel, and these libraries, but much more libraries in the ROC toolkit area, or as you see here, a little bit elaborated also on news on hardware is of course here the graph core, interesting IPU, intelligence processing units, or unique for some of you that don't know about this, it's a quantum annealer, a very specific device as well. So we see much more heterogeneity in the future. And of course, we want to leverage this with the different software infrastructure frameworks and tools. And in this way, we have a very complex setup for users to follow, right? Hence, one of the ideas of the CoE RAISE project we're working on is, can we make it a bit easier for users to define a sort of unique AI framework that at least gives users the first initial hint of how you use the different module environments and all the different systems for the HPC. You basically go to Barcelona, to Jülich, to Riga, to Iceland, and then have different setups, but how we can do in a way that perhaps the porting of all your AI codes and simulation codes is getting easier. These are examples, of course, we're working on based on basically all the experience we have all in these different applications that we would say The application co-design is a very important factor in CoE RAISE to really learn what's really needed for the scientists. But the idea is also that this framework is, of course, not for RAISE alone. It will be open source based on our website soon, that where we basically share some Jupyter notebooks, where we share some lessons learned on how to make a modular environment in a systemic way for Jupyter kernels or Jupyter Lab kernels, for instance. So many of the artifacts will be now dropping off after the project have been running for a year or a little bit more than a year, and we really understand more of these, let's say, AI-approved technologies for exascale. And now what we did in the project a little bit, and if you want to know more, feel free to contact us. We did an initial round on fact sheets to understand and learn from all the use cases, more or less from 10,000 feet perspective. But then we really dived into all of these different applications, essentially with a so-called technique called the interaction room, where we really have, understood and tried to understand what are the data, the real data that is available, of course, always in the light of the specific physics problems or data analysis problems at hand. And what we could derive from this are kind of two things which shapes a little bit our software framework, which is really then the one idea of saying, what are the AI models that matter in that context, right? Not all AI models are suited for all data. So we have to identify which of those matter, and it's a more or less living process, even be trying still things out, like we see today with the graph neural networks. That was not at all clear when the project started. So we have a certain, let's say, momentum of trying different technologies. And here we today in the seminar on graph neural networks, we'll really learn how this materializes with a very interesting new technology, which has lots to offer. So the other part that, of course, then shapes in all of these interaction rooms essentially is then what exact libraries we require, what architectures could help, and where we basically see the move to the future when we think about that quantum devices for optimization techniques in machine learning algorithms itself. Many of those are basically based on optimization techniques. So there we could use maybe quantum devices in the future to solve the optimization problems, come back to us on the general purpose computing, and then have a much quicker result of AI. So this is also something what we explore in the CoE RAISE, and which was tremendously helpful in the interaction room process. If you want to know more about it, these are some examples of the fact sheets, but they will be also soon of our CoE RAISE website, and we have some of them already also published throughout the different use cases. Also, our YouTube channel is, of course, a pointer where we have already lots of material and videos available. Also, many of those are already in post-processing, so will be soon available on the YouTube channel. So I encourage all of you to go there and like the channel and subscribe to the channel. There will be more content coming during the course of the project, which is definitely a good source, including, of course, understanding fundamentals we had in the project, like the interaction room, or many other AI models we already had actually covered in the last couple of months here in the RAISE project. And some concrete outputs, what you can see here for our design processes and also for the lessons learned in the project. You see here, when you come to the matrix that we defined between all the different use cases, on the one hand, you see this. In the beginning of the project, that was rather abstract, but now we have a more fine-grained idea, and we constantly refining actually this matrix more and more as we go in the project with all the different use cases. And then what are the technologies that actually are relevant for all these different use cases? What of those technologies have been tried out? Things like convolutional autoencoders here, for instance, in some of those. Then in others, a residual network, maybe ResNet 50, which still is one part of the convolutional neural networks I was alluding earlier. Or as we will learn today, the graph neural networks, for instance, which have been adopted by a couple of use cases as well. And we will hear about that, of course, after a while here now in this particular seminar. And we will continue in the future, probably talk a little bit about LSTMs, about GRUs. This will be more broadly adopted in the project already, as we know. And many of those technologies are quite interesting. Because we, of course, have the unique proposition that we not only use them, let's say, in the small scale. Usually, we are also using them in a high scale environment. So talking about HPC, but also in combination then maybe with hyperparameter tuning already, things like Octuna or RayTune, where you then automatically have also parameter tuning involved. So that is one output basically, but that of course is very relevant for us shaping the so-called RAISE unique AI framework that you see here. Of course, it's a very loaded slide, but if you want to do AI at scale and then combining it with, let's say, numerical simulations and so on from the more physics area, you need a quite interesting stack here. And I don't want to spend all the time here to go through all the different details. We have deliverables on that. So if you are very interested to see more about the RAISE unique framework, please contact us. We are free to giving out, let's say, much more information about this. And the key message to take away is that today the seminar will shed some light on particular, elements of the AI models we have rather on this level, where we talk about how they can be used as PyTorch, TensorFlow, and so on. And then also, of course, scaled up with some of these technologies. A little bit missing is here the parameter tuning here and there. And in other seminars here and there, we will talk probably also a little bit about singularity, how you can encode, let's say, elements of applications together with data, very simply close to the HPC systems based on singularity, for instance, but also think about more APIs that take ONNX and some standards into account. And as alluding to before, Jupyter Lab and elements of this are already prepared to be also available on our website so that you understand how you can combine these interactive HPC really with cutting edge HPC systems and their, let's say, sometimes really interesting module environment, because some of you know that the AI technologies move very fast. So we have very different versions of TensorFlow, different versions of PyTorch, and those of course have to match the underlying modules of our CUDA libraries for NVIDIA cards and many other libraries which are related. And on the physical sciences, the same way, we have different MPI versions or libraries that need to match the different codes as well. So very interesting material. Obviously, this here is also first draft that you see here, and we will revise these much more now in the, let's say, coming months towards the end of the project, where you probably have many of those artifacts from these frameworks available on our website to download. And with this, I think I'm showing the kind of key essence of RAISE right now. Of course, what I not really showed deeply in is the important part of the applications. You will see two of them today, but of course, RAISE lives also from the important RAISE applications, right? So all the 9 applications I was showing. More information on that on the website. So to stay in time, I will give you just a very short introduction to graph neural networks. As a professor here, from some of my slides I use in teaching. This is not at all totally graph neural networks full-blown introduction, but it helps you perhaps to understand a little bit how it works in machine learning and how you move to graph neural networks there on the one hand, but then also maybe differentiating it a bit with the traditional models that many of you know based on text, based on images or videos. Here we think about much more graph and network structure of data. So hence, it will be just a very quick introduction to understand perhaps a little bit better my, let's say, speakers that will be following after me. We will review some machine learning basics here very quickly. What is now basically relevant on the whole machine learning cycle. That means we have to understand a little bit about the hypothesis set, what the learning algorithm is in terms of error, and so on. So how you progress and how you learn actually from data. And this will be also a very, let's say, short introduction. And there's lots of different material available. If you want to know more, of course, just let us know in RAISE. Then followed after that will be a graph neural network focus, and it's a very big field right now. So basically there I show you some motivation and variance on the GNNs. Of course, the difference to the different data sets that we already were describing in the beginning, and perhaps some comparison with established deep learning models. And I just gave you in the end a little bit, a very short idea of how you can actually use this in a very trivial application called node classification, where you have maybe the similarity of graph nodes together used with a so-called node embedding approach. And of course, from the selected application areas, I just picked one to stay in time, and then we will hear from Leo and from Eric much more how they do it at different areas of sciences within the RAISE project. and more is probably to come within our project in the next couple of months. So looking back at machine learning, and of course, if you have questions to all of this material, obviously we here and there go very fast because it's a webinar that is just 2 hours. We could fill a whole day on these materials. But essentially, when you come here for questions, always put them in the chat. We will reflect on that, of course, later on when we have the discussion Q&A again. So in a way, here you see an overview of machine learning, where you basically have something which many of you know, there's data to learn from, which is the key heart here from the training examples. So this is really something we have to have. It has high demands of storages, especially in basically HPC. If you think about many turbulent CFD runs or so, they can easily fill up very quickly to terabytes, but also satellite data today from remote sensing or from Earth observation satellites can fill quite a bit of a parallel file system. Then the other aspect to it is that in machine learning, we have the so-called assumption. We call that PAC learning, probabilistic approximately correct learning. That means we have a certain assumption that the data that was derived from some probability is the same probability distribution, although we don't force which one, right? We just assume it's the same data set origin, so to speak, where this came from. And it's something that we don't really need to know, but we assume. And in a way, what we really think is there was a function that creating this data, which we know the unknown target function, and to actually try to get close to this unknown target function is one of the goals of machine learning. Can we find, let's say, mathematically something which similarly can explain and have, let's say, a machinery in place to actually get close to this, which would be then our final formula. You see here that G that hopefully approximate F very well, because this is the ideal function we will never know. There's always noise in the training examples. There's something which we mean that 100% machine learning is never possible, right? But to do machine learning requires these two building blocks that basically is now our tool set, right? So this is something which AI people have in their hands. They call it the hypothesis set and then the subsequent learning algorithm. Examples of what you have heard already is probably artificial neural networks here in the hypothesis set, and you learn with them with backpropagation. It's an algorithm and optimization to really learn from the examples that fits to this particular neural network. But we have also support vector machines where you basically use quadratic programming as a learning approach, and many others where basically you see these are your solution tools in order to use the training examples then and actually come to the final hypothesis G that hopefully approximates F well. There's just one more thing. How do you know that you learn, right? Hence, we need an error measure. There's a loss function you have to define that you basically can describe that over time, my error is shrinking so that I know I'm actually progressing and learning. And we see here, we have a very nice scenario of so-called supervised setups where you have vector X with lots of features in the data and always a guiding label. This is a very nice assumption here. It's not always there, the supervised learning approach, but here it's nice that of course from these training examples, we can a bit learn because we have the guiding output. We can learn if it is this or that class, for instance. And one thing I should note is, of course, it was a bit a too trivial assumption. The target function is not really something we are after in machine learning. We call that rather a target distribution, simply because we have some training examples where the same X gives us different Ys, right? And this is just practice out of data, but you know also that this is then not anymore a mathematical function, right? So hence we put a probability distribution around it and say, we assume just P of X given Y. So basically a function of X that is here mapping to Y plus some certain noise in order to work with this basically training examples. Examples is always like a Netflix movie, the same X, the same movie. You rate it once like very nice and 5 years later, you don't like the movie, but in the database, it's suddenly also, let's say, instead of a 5, a -5 in terms of ratings. But let us proceed a little bit towards graph neural networks. So how that works now, how basically go and move towards this is best explained with this hypothesis set again. So you have a certain problem at hand in the application perspective, And you maybe pick then out of this pocket the support vector machines, which would be one of the hypotheses. The hypothesis 1 here as an example that tries to find an ideal line here, for instance, between two different class distributions. And this is something which maybe fit well for one application example. Now, of course, there are lots of parameters involved, which means the hypothesis set is even for SVMs quite loaded, because also SVMs have different parameters, and all of them would be different hypotheses that we have to work with. But the other hypothesis that we pick here today in the seminar would be then graph neural networks. So it's another of these solution tools where we know, okay, there's a hypothesis set and it fits to my data, which is essentially one of the important parts and fits to the data problem at hand that you will also hear in one of the later approaches. So the graph neural network, of course, I think is in a way simply pretty obvious, because you already know from the name, it obviously has something to do with graphs, right? So essentially, you would assume a general principle of having a layout of data that more or less is a bit unstructured, in the sense that it's not a simple, image, but pixel by pixel or a certain sequence of words. Here we have a maybe dynamic growth in a social network, for instance, which always can be mapped as a network of sort, because it's very unstructured in a way how it grows, how new, let's say, nodes, which could be people's or profiles, really in Facebook, for instance. So starting then with graph neural network is exactly this. So you have a motivation that some data sets are just not, let's say, the kind of quote unquote simple structure that you know from these images. You have quite an uncertainty in the idea of how the size of this graph will grow, right? Some have very family bound basically behavior. So maybe in social media, you would have the family tree grows well. Others have, let's say, lots of high school, international traveling, and interesting friends there. So the growth of these networks, for instance, in social media is one good example, is very variable. It is very not uncertain in the future. Still, you have to deal with it if you want to do some analysis of the data. Images, on the other hand, if you go to basically different ones from ImageNet, but also cutting edge satellite images, where you maybe want to do pixel by pixel wise classification of understanding if it's a water, if it's a train track or a building, etc. The structure is, of course, much more homogeneous. It comes from a satellite, Earth observation satellite, that really takes a picture, and then you take a patch out of this large data set and you can work with it. And the general idea is that you have a pixel by pixel structure. If you don't have that, it would be hard to use some of the traditional elements partly that you actually use for this, like the convolutional neural networks, which are in a way very perfect for these structures, because they preserve a little bit the spatial connectivity. For some of you that know from GNNs, it has a so-called receptive field, mimicking, so to speak, the human behavior in the brain and in the eyesight, and moving over these images, and always preserves a little bit the neighborhood, right? And with this, for instance, for satellite image analysis, this is very good. But of course, we have many other application fields for image detection in ImageNet. It's a cow, a car, or whatever. The convolutional neural networks are just simply good at. Equally, in many of the phones today about language translation, languages at all, and natural language processing, NLP, you have things like long short-term memory, sequence models that are very brilliant to deal with text. But text follows also a very certain structure. There's a sequence of basically characters. And the same goes, of course, for other sequences, which are maybe more a sinus wave or so. In the end, it's also sequence. So we can have a time series data, for instance, of sort in one of the application domains. But in a way, you would have the time steps, you have your way of how to deal with the data set, which is rather homogeneous again. And hence, you more and more understand, I guess, why now the idea of graph neural networks is how we can deal with data which is not actually like this. So how we can find patterns still from this data, but of course thinking more about maybe neighborhoods or subgraphs, who of the nodes, when you think now about Facebook profiles as a simple example, who of the profiles are actually very close together and could form a neighborhood. So these are, of course, also interesting ideas that advertisers can use in Facebook to determine where would be the most profit of switching to certain advertising options. And so in this sense, the graph neural networks are perfectly suited for that, where you have lots of interdependencies of these objects, which maybe from the image, would you say, is not at all given when you have the left side of the image on the right side of the image, might not be very much connected, but on the graphs, one line, one edge could be simply reconnecting a node which is on the complete other side of the network of sort. So these are the dependencies which are really lively and subject to change. And in the end, this non-regularity of this data structures is something of interest, which we really want to work with. And so this would be one hypothesis that you take out of the hypothesis set now and to put to your data set in question. I always gave the social media as an example, but I will come later also to other ones. But of course, a complete introduction to graph neural networks would take 2 or 3 university lectures, and we don't have that. So we take here a little bit simple assumptions. Molecule data sets, for instance, might be another one. Now, how that would work? You have a very specific AI model, so to speak, for a very specific problem. I already was alluding to that we have this interesting convolution ideas with GNNs really moving over this kind of images, for instance, that you see here as an input image, and then you have so-called feature maps and pooling layers that more or less subsample some of the data sets, and in the end do a very good job. And as I said, also when you have graphs, this structure is not really anymore given, and just moving over this spatially localized idea of this receptive fields and so on might not be the best idea. So instead, the graph theory as one approach really in this area is doing so-called node embedding. So usually this might be also a couple of much more slides I have time to present today. But the key essence to take away is that really it learns a sort of encoder from the input network that you give here into the network. And from that, the encoder, and that is what you learn with machine learning, these encoder structures, it would learn a way of making, let's say, a very dense representation of this neural network, of this network that you have here in order to encode the nodes and preserve as best as you can the neighborhood there. So you would have a much more low dimensional representation. Some call it also latent space again. And here's one example where you can use what you can use perhaps with a similarity measure there to think about that you can actually use these encoders and try to have these different nodes here, U and V, a similarity measure defined so that in the embedding node space, they may be still very close together because they have a connection here basically in the graph. And when you map this, you can use, of course, this mapping then for interesting applications. If you consider, for instance, node classification, very simple that here this U was basically labeled before. We know exactly what the label of this particular class would be. Then the assumption could be, because there's another V very close to it, that it probably follows the same class label. Just one example of applications. Hence, you have another hypothesis that you put out, and here a very precise one out of this graph neural networks, which could be very many, and you will hear from basically from Leo and also from Eric that there are very wide varieties of these models. And this is just one example, which is relatively straightforward, where you have a so-called encoder and decoder strategy, where you first encode a little bit in this embedding, then the idea of this pairwise structure from different nodes, where you have an embedding or a vector really of these embeddings with really dense representation. But then you decode this embedding again to a sort of neighborhood based on the similarity function you define. Let's say we define the Euclidean distance, but doesn't have to be that way. It could be other similarities, categorical elements, and so on. But the key message is that, of course, in a way, it defines a little bit what we want to have as a final hypothesis. What I really want to learn now with machine learning would be then, how is actually this encoder and decoder looking like, right? And for doing so, I was alluding to, we have a certain learning algorithm, which needs then a certain error measure and a loss function to think about. So here, the loss would be clearly thinking about that this decoder in a way should be approximating the similarity between these different two nodes. V is not given here, but assuming it will be one of the neighbors here, we assume that basically here the decoder will be learned essentially from this embedding space, then to hopefully approximate the similarity of UV almost correct, right? And you can knock down this error using optimization techniques. And this is just a pairwise node relationship approach. There are several others. And hence, I want to actually, at the end of my talk, more or less, also point you to this book. So, of course, this was a very short introduction to GNNs, but I hope you get a little bit of meaning how that could work and how you can learn from these data sets. A very comprehensive book I would recommend to you is this Graph Representation Learning from Hamilton. It's actually also freely available, although there's also a kind of preprint only. So if you want to have the real book, you should basically go ahead and buy it. In the end, just some application areas. And I think I just leave it here. Pick one, what was the node classification, where you have already a couple of labeled samples within the nodes of this interesting network. And you don't know what really the label is of the neighbors in this network, but with this approach of basically learning, so to speak, the encoding to the latent space, and then from there, the decoding into basically a way of a very neighborhood or similarity measure based neighborhood, then you can also start labeling your neighbors based on this information. And it's actually very good to do so. In a way, we would call that a semi-supervised way to learn this, but definitively helps. Let's say if you have a very large graph, which is now the point in all of that, you don't have this little graph that I showed you there, a very complex graph, a huge graph, then of course these algorithms are just beautiful for this. And there you can go on and go on, categorizing documents with natural language processing, social network analysis, obviously like Facebook or Netflix users. This is all elements where there's lots of money in the game also for companies. And actually it could be used for graph clustering. Subgraphs could be identified based on these things I just mentioned roughly. But I think now is the time also to take no more time for this particular presentation, but rather dive into the scientific application space that we have in the RAISE project. So here we will start a little bit with how you can now use graph neural networks and very specific ones of those for numerical simulations based on known physical laws, and then also another more data-centric approach for particle reconstructions at the Large Hadron Collider. Some references, but I think the book from Hamilton is really the best I can recommend you right now. And obviously it goes without saying, these technologies and tools are also nicely supported by now in TensorFlow, for instance, of course, as well. So I think I stop sharing here. Again, if you have questions, please put them in the chat. We can come back to that later. And I would stop the screen sharing here and would invite Leo to share his slides, please.
Yes, thank you, Maurice. I'm sharing. Okay, let's go. Do you see my screen?
Yeah, it works very well. Thank you very much. So Leo, take it from here.
Great, thank you, Maurice. So thank you, everybody. I am part of the I4CM team in the Atos partner of this Center of Excellence RAISE, and we are very glad to be here at this training, if we must say training and not seminar, if I understood well. So what I am going to present now is graph neural networks for the specific subject of numerical simulation. I had a small introduction about graph neural networks, but I think Maurice did a great job introducing what they are. Hopefully there won't be so much repetition. Actually the motivation to use graph neural networks in the field of numerical simulation is obviously the fact that a mesh used in numerical simulation is actually a graph. So we'll start from this point. So what is actually a graph? If we are doing computational fluid dynamics, for example, we use meshes. Basically, a mesh is a graph that spans the physical space we want to, in which we want to simulate some physics. So on the right, you can see a figure. I took some figures in this talk. There is always a reference at the bottom of the slide. So on this figure, you can see an airfoil in white, and we are looking at the way the fluid goes around this foil. So for this specific example, we are talking about the air, and the mesh is going to span this physical space. And on this specific example, you can see that the mesh is not regular like an image. It has different kind of cells. In this specific case, they are all triangles. For the cells are all triangles, but of different sizes. We can see that on some regions, the mesh is finer, whereas on other regions it's more coarse. It's coarser. So this mesh is actually a graph, so a set of vertices that we call them nodes, and a set of edges. The edges can be directed or not. We will consider case where they are not directed, but we can easily expand to the case of directed graph. On the mesh, this graph, this specific graph, it will be able to carry features. So we can add some features on the nodes or on the edges. These features you can think of physical variables, for example, the local temperature at this point, or the local velocity on the X or the Y axis, and so on. And finally, we will also add the coordinates of the node to these features. We will add the coordinate, for example, in 2D or 3D underlying physical space. There is a small point which is interesting to note. Tobias Prof in the paper which was published recently clearly made the distinction between the two spaces, because at this point we have a physical space that we will call a world space, which is the space in which the physics unfold. But we also have defined another space, which is a geometric space, the space of the mesh. And so it has its own metric, and the mesh actually defines a manifold, which is embedded in the world space. Okay, so the motivation to use GNN in our case started from a specific use case, which is part of the task 3.3 of the CoE. Basically, the idea is reactive flows. So we are considering combustion inside a rectangular combustion chamber. This is something which comes from our partners at the CERFAX. I think some of them are present right now. So briefly, this use case is quite simple. We have this rectangular textbook case chamber, and we want to we want to learn the relation between the states of the reaction and the combustion rate. So what our partners at the CERFAX did is that they carry out some GNNs simulation, which fully specified the physics, very costly simulations, and then they extracted some features of interest on a coarser grid. So this grid will be interesting for an LS solver, for a larger scale solver. So basically, we filter out a progress variable and the flame surface density, which is our input. And the point is to learn the mapping between this input, the progress variable, and the output, the flame surface density. Since in this specific case, we have a rectangular combustion chamber, we can use a very simple grid, a mesh, which is Cartesian, regular, like an image. So it's some kind of 3D image. Just think of voxels instead of pixels. So this things works quite well. We can use state-of-the-art architecture for the CNN, like a unit. But how do we generalize to irregular meshes? So that's the point of using GNN at this point, and to a combustion chamber that won't be rectangular, but more industrial realist, like an annular combustion chamber. So basically, in CFD, meshes are irregular, meaning that you have different size of cells, and also each node can have a different number of neighbors. So we call this the degree of the node. If you want to directly apply CNNs to this kind of meshes, the naive way will be to interpolate this mesh onto a regular grid. The issue with this strategy is that we will lose a lot of information if we don't take the finest scale as a scale of our grid. So by taking this specific scale, the smallest scale, we will end up by dividing the large cells into a lot of different cells. And so we create a lot of artificial, non-essential new cells. As an example, if we are in three dimensions, and if the bigger cells are like 10 times greater than the smaller cells, we will end up adding 10 to the power 3 new cells. So obviously it quickly becomes intractable. So at this point, we can use this simple use case as a benchmark for our GNNs, but in the end, we will use a realistic mesh, irregular mesh to benchmark the GNNs. On this slide, you can see figures that shows the pipeline if we use such an interpolation step. Basically, the idea is that once we have trained a neural network, we want to couple this neural network with a numerical solver, like an LES solver, and we will have to add this interpolation step in between, which takes into input the mesh and interpolate it into a grid, and then outputs the tensor, which is fed into the inference engine, and then it goes back and forth. We have a GNN inference engine. The pipeline is streamlined. We don't have this interpolation step since the GNN directly handles the mesh, which is a graph. So that's the interest of GNNs. So in this section, I will talk a bit about GNNs. Hopefully, it won't be too redundant with Maurice's brilliant introduction. So very briefly, GNNs, they handle graph natively. And we put the feature vectors on the nodes or the edges. And therefore, we want to process the spatial structure, which is the graph in itself, but also the signals, which are the features carried by this graph. An important point to keep in mind is that, as Maurice said, most of the graphs most of the data we want to handle with GNNs comes from very unstructured sources, like the internet, for example. We have a lot of data coming from social networks, and they look like the graph that you can see on the bottom right. They are very clustered, whereas in our case, we have meshes that are less irregular, let's say. They are more structured. We can see a mesh on the left. Basically, the degree of the nodes is more homogeneous. You don't have a constant degree throughout the mesh, but it's more homogeneous. Also, you only have local spatial correlation. In general, you don't have a node which is connected to another node which is far away in most of the machine. Also, in the literature, you often find GNNs that are benchmarked against another on this kind of problems like classification, semi-supervised classification. For example, you have nodes that have labels and other who don't, and you want to label them. You have a lot of frameworks like the inductive or transductive framework. This is not things that are interesting for us in the specific case of meshes. In the case of meshes, we want to regress physical fields or variables. So we have, let's say, a progress variable which is stored on each of the nodes, and we want to regress this variable against the combustion rate on the same node. Okay, so let's dive a bit more into the details of GNNs. So basically, GNNs work by propagating information inside the structure of the graph. So this is called message passing. This is a very generic term, but this is the very basis of GNNs. The idea is that on the top right, if you can see this X2 node, it has a neighborhood, let's call it a one-hop neighborhood, meaning all the neighbors that are one hop away from X2. It has three neighbors, X1, X5, and X6. We want to pass information from these neighbors onto X2. So there is some kind of function, let's call it G, that aggregates this information. Basically, this idea is really similar to what we have with convolutions in the case of CNNs. Basically, a convolution has a receptive field. It looks around its center. And this is quite analogous to a convolution. So we will define this GCN layer, graph convolution network layer. The idea is really to aggregate the information locally. Basically, this layer will process this convolution over the whole graph simultaneously, meaning that we will aggregate information of the neighbors onto each node at the same time. And then once this thing is done, we can just, as we do in deep learning, we can stack these layers. We can stack GCN layers in order to capture spatial correlation that are far away. Basically, if we have K layers, K GCN layers, we can capture information in the K hop neighborhoods, meaning all the nodes that you can reach with K different hops. So you have this receptive field which is growing. The deeper you go, the more global you go into the graph. Okay, so this slide is a bit tedious. Basically, I want to show you how it works under the hood, how we can define this specific GCN layer. So basically, when we talk about graph, we often think about the adjacency matrix. If we have n nodes into our graph, we will consider a matrix with n by n, which is the adjacency matrix, and it encodes whether there is an edge at this between these specific nodes. So between the node I and the node J, the adjacency matrix will give us the information whether there is a node or not. For normalization purpose, we will add self-connection, meaning we will add a small connection to each node with itself. So it means that we add the identity to this adjacency matrix. Then we will normalize this adjacency matrix with the degree matrix. So this is the degree matrix is just a diagonal matrix which stores the number of neighbors, the degree of each node. So we work with this normalized connectivity that you can see in the center, and these things really encodes the connectivity of the graph. So now basically we want to propagate through the network a signal. The signals is all the features that are stored and which will evolve throughout the network. So at some step L, we will code HL all these signals. So basically, this is a matrix, N by D. N is the number of nodes, and D is the number of features. So these features are learned. You can think of channels in the case of CNN too. And then the layers. So to get the next signal, you will multiply your connectivity by your signal and by a trainable weight matrix. So this matrix W is going to be learned. So this is the weight and biases of the layer that you want to learn. And obviously you add some activation function, nonlinear, as a standard as is ubiquitous in deep learning. So that's one way to define convolution. This is a spatial way. There are other ways to do this using spectral method, but basically the idea is always the same. You want to propagate this information locally, just like convolutions. Okay, so to finish this small introduction on graph neural networks, so I want to insist on something Maurice already insisted on, which is the fact that in most machine learning problems, you have this distinction between the spatial structure and the signals. Basically, if you take computer vision images, the structure is the grid on which the pixels are pinned. And the signals are actually let's say RGB, red, green, and blue. And so in the case of GNNs, it's clearly decoupled. So you have the spatial structure, which is the graph in itself with its edges and nodes. And also you have a signal, which is a physical field, which is stored on the nodes and on the edges. If you take the case of natural language processing, the spatial structure is more the order of the words, the tokens, which correspond roughly to grammar in linguistics. And the signals, you can see the signals as the semantics of each token. So like word embeddings and these kinds of things. So that's an interesting thing about GNNs. It clearly decouples the two. When it comes to the pros and cons of GNNs, in our case, when learning physics, GNNs offer to capture the multi-scales of the physics. Basically, if we take a mesh with different scales inside this mesh, we will force the GNN to capture these different scales in the physics. Another point is that we can dynamically change the mesh throughout a simulation. The turbulence, for example, a turbulence can move throughout the space, and therefore the parts of the physics which are complex, which are difficult to capture, can evolve. Therefore, we can evolve the mesh, we can remesh in order to follow this complexity and capture all these important areas. Also, it natively interpolates, so we don't have this cumbersome interpolation step in between. When it comes to the drawbacks, actually, we are struggling with the memory when it comes to training a neural network, a GNN. They are quite tough to train and memory intensive. So we are working on this issue with profiling, some kind of memory profiling. I will go a bit later into the details by using the PyTorch geometric as a support because we chose this library. This is a good library which is built on top of PyTorch, and it offers a lot of basic tools, not so basic tools also for GNNs. So basically, PyTorch geometric, or you can call it PIG if you prefer. It's not really nice, but that's the name. PIG is based on PyTorch. It provides geometric deep learning tools. We call it geometrics because graphs are actually a geometric manifold. This is a part of what we call the broader field of geometric deep learning. And also, the idea of PIG is to be based on sparse matrix operation because the adjacency matrix of a mesh is really sparse, and we don't want to expand this full adjacency matrix in memory. This will be a huge bottleneck, and obviously we want to capitalize on the hardware acceleration. The main modules you want to look at is the neural networks module, which is an implementation of a lot of state-of-the-art architectures, and also the loaders module, which is interesting because under the hood, when it comes to GNNs, you have a lot of operation to send these graphs into memory to encode them into tensors in an optimal manner. So the loaders are doing this job of taking these graphs and converting them into tensors that the GPU can handle. Okay, so another point which is crucial is batching. So when we do machine learning, we obviously want to batch our data. The point of batching is actually when we build the memory, the model in memory, we want to take not a single datum, but a lot of different data. The point of which is twofold. First, we are going to use the GPU acceleration by making all the information on all the data at once, and also we will reduce the variance of the estimator of the gradients. So that's also really interesting. In our case, we have an issue because the meshes are really huge. We can have thousands of or even millions of nodes, and this is really too much for most of the GPUs in terms of memory. So in some experiment, we could not resort to batching. We only had one mesh at a time. The whole mesh was our datum. So this was a problem when it comes to the variance of the gradients, because the gradient was really variant and hard to stabilize a training. So an idea that we are currently exploring is to divide the mesh into subparts. Basically, we have sub-meshes that maybe overlap a bit to handle the side effects, but these meshes are considered independent, meaning that on the adjacency matrix side, this independency will end up giving a block diagonal structure to the adjacency matrix, and this is interesting when it comes to sparse encoding. You can the compiler can optimize this kind of structure in the memory. Okay, so on this slide, I'm deep diving a bit more onto the theory, and I'm using the PyTorch geometric Riedel doc, which is really nice for this. Basically, PyTorch geometric is based on a specific framework of GNN, which is called message passing. The idea is to generalize a lot of different GNN architectures. So I'm going to briefly present this framework. So it covers a lot of the architecture, as I said. So basically, you have three different functions. The first function is called a message function, phi here. It's going to take the information of the neighbors of the node. So if you have a node I, you're going to take the information of all the different neighbors, J's. You're going to take this information and apply some transformation on it. So that's the transformation called message. We call the message function. Then once this is done, this is dependent on the degree, which is different at each node. So we want to aggregate this onto, let's say, a vector of features. So we will use an aggregation scheme, and we want this aggregation scheme to be permutation invariant. So we don't, in this framework, we don't want to use the information of the orders of the neighbors. If we shuffle the orders of the neighbors, it should not change the result. So such aggregation scheme can be a simple summation or mean and average, things like that. And once this is done, we have aggregated the information of the neighbors. We want to update the state of the neighbor, the current state of the neighbor. So we will use an update function called gamma here, and to make this update. All these three functions must be differentiable because we are going to wrap them up into layers, and then we are going to stack these layers into a neural networks, and then we are going to retropropagate the information throughout this network. So we need this differentiability to compute the gradients. This is basically the framework that PyTorch geometric offers with a base class called message passing that supports this mechanics, and you just have to implement the different methods of this class to subclass it to define your own architecture. Okay, so let's finish this part by a small point on the complexity of what is going on under the hood. So basically, if you consider a mesh with n different nodes or cells, the adjacency matrix, in the general case, can be of size n by n. So that's obviously too much to handle in memory. But in the case of meshes, as we saw, most of the time you only have the d times n edges on average, where d is the average degree over the mesh. And so we want to rely on sparse data formats in order to store this adjacency matrix. We will never store it fully expanded. Pig use an attribute which is edge index, and it simply stores this connectivity into the coordinate list format, which is just a sorted list of the edges with the description of just the index of their two nodes. So there is a light footprint. But all this thing comes as a cost, which is the data loading. When you do the data loading, Pig does the jobs of expanding everything into the most optimized tensor representation, which can be handled by the GPU. Okay, I have no idea of the time which is left.
It's okay. We have still 40 minutes. No stress. I think Eric is around 20 minutes. Go ahead. Go ahead.
Okay, great. So a small slide to announce that we in the team, the I4CM team, we plan in the coming days, maybe weeks, I don't know, to open source our model collection. Basically, the idea of this repository is to provide the data scientist and the physicist with all the tools to define models. We are really on the model side, not on the integration, rollout, coupling side, really on the top of the stack. So the idea of this model collection will be to implement all these GNN architecture, all these physics-informed losses, the kind of thing that we do in the team and in the Center of Excellence RAISE. We will use the PyTorch Lightning library. For those of you who don't know it, that's some kind of nice syntactic sugar on top of PyTorch in order to avoid redundancy in the code and to provide a very lightweight framework to run experiments. So once the code is open sourced, you will be able to find everything which is described in this talk in the combustion/GNNs pipeline. Okay, I have a last part. I can go briefly over it, which is an annex of various architecture to make things a bit more concrete. Basically, so far we talked about GCNs. So the GCNs are the building block of these graph neural networks, and these are layers that only modify the signals that are carried by the graph. But we can also define operators which work on the structure of the graph in itself. For example, we could think of an operator which will add some edges, delete some edges, delete some nodes, or whatsoever. So that's, I'm going to briefly present a graph unit architecture, not because it is interesting in its result, in its efficiency, but more because from a theoretical viewpoint, it is interesting to see the different kind of operators that you can fit together in order to build this rather complex mechanics. So basically, the idea of a graph unit is to mimic the units. We already talked a lot about units. This is a state-of-the-art CNN. And the authors, Gao et al., they wanted to mimic this structure. So basically, you take a graph in input, and you apply some GCN instead of the convolution. So when in the standard convolutional neural networks, you apply convolution, here you're going to apply our graph convolution that we defined previously. So this only applies on the signals. Now we are going to define another kind of operator which works on the structure in itself, which is the pooling G-pool operator. The idea is to reduce the size of the graph. So we will prune this graph, we will remove some edges, some nodes, and I'm not getting into the details, but you can think of it by contracting the graph, taking only the part of the graph which are of interest for this specific task. And then we are going to alternate this GCN and G pooling to reduce this graph into a very minimal subgraph, which is really dense in information, just like a latent space. And then we have, so this is kind of an encoding part, and we have the associated decoder, which is the exact opposite. We unpool back to the original structure. So by unpooling, we mean that we restore the structure that we had previously. So this is analogous to the skip connection. We just take the structure and restore it. And we use the signals that are coming from the GCNs from the latent space. So we restore progressively, we restore the structure of the graph, but the signal has changed. So basically, if you want to regress between physical fields, like on one hand, a filtered progress variable in combustion, and on the outside a combustion rate, like a frame surface density. You can use this kind of architecture. We did this. The structure is interesting. We had nice results when it comes to the precision, but this architecture is too heavy, too cumbersome. So the memory footprint is really high, and it's low to train and low to infer. So there is another architecture which is older age, which is really I think one of the best on the different benchmark, which is called graph attention. It used the mechanism of attention coming from natural language processing. I'm going really briefly on this, not getting into the details of attention, but you can think of each node learning to find the relevant neighbors. So it's not weighting all its neighbors the same way, but also it has some kind of implicit weighting scheme which selects the interesting nodes, the ones which carry the information. So basically, all of this is taken into account. You have this attention head which learn which neighbors are interesting. Then you normalize this with a softmax, and then you aggregate. You make the aggregation, the non-linearity, and you end up packing this whole thing into a message passing into the message passing framework. You can have several attention heads to increase the efficiency, and you have this GAT architecture. For the moment, this is one of the most interesting architecture. It's really fast to compute because you don't have a matrix inversion. Many architectures in GNN relies on inverting matrices. This is not the case with this one, and also it natively handles irregular meshes, and it's quite efficient when it comes to cost and memory. So I think that's it for my presentation. I think we will keep the questions for the QA session at the end. Thank you very much for listening.
Yeah, thank you very much, Leo. Excellent presentation. Also very nicely illustrated and with an interesting comparison really with the numerical meshes that we know from the very traditional models in the simulation sciences. So in the light of the time, I think, thank you very much again. And questions, please already start in the chat. There are a couple of them already, I think, in the chat, but we will pick on them in the Q&A session. So Eric, if you are there, then I would invite you to basically share your screen. And now we switch from the company field to the Large Hadron Collider activities that we have at CERN, basically in Geneva. So Eric, take it from here.
Thank you very much, Maurice. So to start with, I'll just ask the usual question these days. Can you see my slides?
Yeah, sorry, absolutely. Works.
Great. Okay, so hello, everyone. As Maurice already mentioned, I will be talking about graph neural networks and how we use them for something called particle flow reconstruction at the Large Hadron Collider here at CERN. So since most of you aren't from the high energy physics field, I'll start with a little introduction about the CERN Large Hadron Collider. So this is the world's largest particle accelerator. It has a circumference of 27 kilometers, and it's located at the border between France and Switzerland, just outside of Geneva. You can see it in this picture here, and it's actually in reality about 100 meters underground. So you wouldn't actually be able to see it from this point of view, but we've painted it here for you. So this machine accelerates bunches of protons to 99.999999% speed of light. And I didn't actually know this before, but I computed that this means that it's about 10 kilometers per hour slower than light. So it's very close to the speed of light. Now these proton bunches are made to collide at different points around the ring. And when they do, some of the protons inside these bunches collide with each other, So there are multiple proton-proton collisions per bunch crossing. And what we call a collision event is all the data that we gather from all the collisions in a single bunch crossing. So we will talk a lot about collision events. Sometimes I just call them events. And then I also want to mention that there will be an upgrade of the LHC called the high luminosity upgrade, which will increase the number of collisions per second, and thereby also the rate of data production. So this is the source of many challenges for the high energy physics community in the coming years, to have a way to deal with all this these enormous amounts of data that will be produced. So in order to actually get this data, what we use is, of course, particle detectors. So from the high energy collisions, from these proton collisions, they result in the conversion of energy of the colliding protons into a cascade of new particles. Now, most of these particles are unstable and decay quickly, and eventually you only have stable particles left. And then these stable particles are the ones that interact with the detectors. So the unstable particles decay extremely quickly in most cases. So these stable particles leave signals inside the detectors, and here to the right you can see an example of what an event in the CMS detector at CERN could look like. So we have things like tracks from the tracking detectors, we have energy deposits from calorimeters, and so on. So these particle detectors can be extremely complex, and they have many sub-detectors. So here I'm showing you a transverse slice through the CMS detector, and here the particle collisions would take place here at the very left of the detector, and then particles travel through here and interact with different parts, leaving things like tracks and calorimeter clusters. So then what we can do is we can combine the information from all these different sub-detectors into a particle level interpretation of the event. And what we call event reconstruction is this process of inferring higher level physics objects like particles from detector signals. So just going a little bit deeper on that point, you could also say that event reconstruction attempts to solve the inverse problem of the particle to detector interactions, or in other words, going from detector signals back to particles that gave rise to them. And in particular, there is something called the particle flow algorithm, reconstruction algorithm, which takes clusters and tracks as input and gives particle types, so electrons, muons, whatever, and momenta as outputs. So this is what this figure is supposed to represent. We have here to the left some kind of physics happening inside the detector, and we have then the detector giving us some kinds of measurements, which are represented here as tracks and clusters. And then we use particle flow to go back from this these measurements into a physics interpretation, which we then can use for various types of analysis. So this event reconstruction is quite compute resource intensive, and this problem will only get worse after the high luminosity upgrade. So actually then it's expected to take up around 60% of the compute budget of CMS, according to 2020 estimates. And therefore there's a lot of work going on in different ways to reduce this computational footprint. And the possible solution here could be AI algorithms, which are easily accelerated by hardware such as GPUs or FPGAs. And we want to use these to reduce the computational footprint and potentially even improve the physics sensitivity, but at least maintain it. So that brings us to what we call machine learned particle flow. So as I already mentioned, we have the traditional particle flow algorithm, which has been around for quite some time, and it attempts to reconstruct all stable individual particles from collision events by combining information from different subdetectors. And then we have our still relatively new machine learned particle flow effort, which aims to replace the traditional algorithm with a more efficient graph neural network based algorithm. Now, there was already a first baseline of this model published in the beginning of last year. All the code is freely available on GitHub. There has also been talks by both myself and my colleague Joseph Pata at the ACAT conference in November last year. So I'm not sure if the slides will be available somewhere after the talk, so you can access these links. But if not, feel free to contact me in case you're interested in looking at any of these links.
We will collect the slides on the RAISE website. I think that's the plan. Yes, okay. It will be available.
Great. So before looking a bit closer at the MLPF algorithm, I just wanted to quickly show the kinds of data we use. So we use simulated data for this, and we give something we call PF elements as inputs to the model, and our ground truth is the PF candidates. So PF elements and PF candidates are just the names for these data structures as they are called in the reconstruction chain of algorithms that are being used at CMS. So the blue part here is the MLPF algorithm, which will replace these green parts. So the important thing to take away here is that we're using the existing particle flow algorithms output as the ground truth, which isn't ideal, since that would make it very hard for us to improve upon the traditional algorithm's performance. So using what's called the generator level truth, which is taken more directly from the physics and detector simulation, would be much better, but this is left for a future study, and actually we have already started working on creating a data set like that. So our data consists actually of a number of sub data sets. Two of them are so-called physical samples, which actually simulate proton-proton collisions. And then we have what we call gun samples, which are just a sort of a made-up simulation where you shoot single particles inside the detector. For instance, we have electrons or muons or pions that we shoot in there and see what happens. So we use these in order to improve in part to improve the generalization of the model for these kinds of particles that may not be produced very often in the physical data sets. Finally, we split the data sets into training test sets as usual. So then let's have a little bit of a closer look at the MLPF algorithm. So in this sketch here, we have element-wise layers in blue, we have graph layers in green, and we have some untrainable layers in gray. So the model starts with the fully connected feed-forward networks for encoding. We also have the same kinds of networks for decoding at the end. And in between here, we use two stacks of what we call combined graph layers, which are custom layers that I will go into more detail on in the next slide. But in short, they are used to both dynamically build graphs and to perform message passing. So we have two stacks of these, one for momentum regression and one for particle classification. So then looking closer at this combined graph layer. So here, this entire large box in the middle is what was represented as a green box in the previous slide. So what happens inside here? Well, we start with a learnable embedding layer, which gives us a flexibility in the graph building. Then we have two layers doing binning of nodes into local context areas and building the graph in each bin. So all of these graphs are disjoint, but together they make up the entire collision event. After that, we have one or more graph convolutions before the elements are unbinned again and returned. So by using this kind of binning, we actually are able to keep a linear scaling of the input size, of the runtime and the memory usage with the input size. So we see this as a key feature because at the HLHC we will have so much data to handle, and each collision event will be very large. So this is a very important feature of for us of this model. So that's what I'm showing here basically. So these tests was done using a single stream on one GPU. Basically, you can see it as using a batch size of 1 on a consumer grade NVIDIA GPU. This is not at all a production-like setting, but in any case, it shows that we have an approximate linear scaling, which is what we're after. So let's look a bit at the model training and optimization. So we do a lot of hyperparameter optimization of this model. So most of you are probably already aware, but I'll go through this slide quickly anyway. We often refer to this as hypertuning, and hyperparameters are of course the parameters that stay constant during the learning process, or at least most of them do for most of the time. And they define things like the model architecture, so the number of layers and so on, or parameters in the optimization algorithm itself. So for instance, the learning rate or the batch size. Now, hypertuning using complex models or with large data sets is very compute resource intensive, and it's partly due to the fact that there's basically an infinite amount of different hyperparameter configurations to try out, and also due to the fact that it takes quite a lot of time to evaluate every single one of these, or to even evaluate one of them. So therefore, we are in great need of HPC resources, and also in need of smart and efficient search algorithms. So we use these resources efficiently. So therefore, we use several different kinds of these to do large-scale hypertuning on HPC systems. And the tool of choice for this that we have chosen is the RayTune framework, which is an open source tool for a multi-node distributed hypertuning. And the reason we chose this is because it has many built-in state-of-the-art search algorithms, some of which I list here. And it also has great support for modern frameworks like TensorFlow and PyTorch, and also integrates well with other hypertuning tools. And we found that it was quite easy to integrate into HPC systems. So here I'm showing you a couple of examples of the kind of hypertuning we did. And so I want to say thanks to Forschungszentrum Jülich and San Diego Supercomputing Center and the Flatiron Institute for allowing us to use their HPC systems. So for what I'm showing you here, we did 2 stages of hypertuning. One run on the GWAS booster at FZJ and one at CoreSite at the Flatiron Institute. So both of these machines have 4 NVIDIA A100 GPUs per node, and we're running the hypertuning using we're running one trial on each node, utilizing all the GPUs in that node. So we did 2 stages, as I said, with different hyperparameter tuning algorithms and different search spaces, as you can see here to the right. And in total, this used up about 76,000 core hours, which if you do a little back of the envelope calculation, you will see that it would have taken around 6 months on a single GPU. Now it took around 83 hours using these HPC systems. So this really shows that the HPC systems are really essential if you want to do this kind of large scale hypertuning. Now, finally, when we found our best hyperparameters, we retrained the model 10 times to see if it was just a fluke or if it was actually good hyperparameters, and it turned out it was. So as you can see here, the loss curves were found not to vary very much between trainings. Same goes for the accuracy curves here. So we were very happy with that. But then, of course, you might ask yourselves if all this hypertuning was worth it. In order to check that, I did some more retrainings, but so this time only using the physical data sets. So none of these GAN sample data sets that I mentioned before. This is just to speed things up a little bit. But so I did 10 retrainings with the hyperparameters before tuning and then 10 after. And here you can see the comparison between the loss curves. And as you can see, the mean validation loss decreased by quite a lot, almost a factor of 2. And this is even though even before we did the hypertuning, we had done quite extensive manual tuning, let's say, of the hyperparameters. So it's not like we started out with a set of really bad parameters. They were already quite good. So we think this improvement is very nice. So now moving on a little bit to the performance that we see in the test set, which is perhaps more important than just looking at the loss curves. So starting with the classification accuracies, here is a normalized confusion matrix, which, as you can see, has a very nice diagonal with ones all across, except for the last class here of new ones. Now, we should note here that this only includes particles that were classified to begin with, so we don't include any false negatives in this confusion matrix. But don't worry, we'll look more at that on the next slide. Here to the right, we have some comparisons between the traditional particle flow reconstruction and the MLPF. So these are 3D visualization of the events. And this is just to show that on a broad scale, these look very similar. Of course, it's hard to see that if they're exactly the same or not, and they are not exactly the same. But the point here is that we see that we overall get a good reconstruction out of this. So looking a bit closer at some distributions here of the transverse momentum PT and the pseudo-rapidity eta. So these are variables that are often used in different kinds of physics analyses. So here again, we're comparing the particle flow with the machine learned particle flow and plot the different distributions for different classes here on top of each other. So we have like the total number of particles versus this variable. So we have a distribution. So overall, we see good correspondence again between these two algorithms. And if you look closely, you can see that there are some differences though, maybe most notably in the electron distributions at low eta values here, where the MLPF seems to be missing a few electrons. The same goes here for low PT values for electrons, which are these the brown dots and lines. So this is something that we're working on to improve. And that brings me to the next steps, which include to create, train, and hypertune on larger data sets. And here we're aiming for a 10 times larger data set than we have had up until now. We also want to define a new generator level ground truth to overcome these limitations of having the traditional algorithms output as the ground truth, which I mentioned previously. We're also looking at adding additional input features. So there could potentially be information from the detector that is available that we're not using that could still be useful. So we're looking at that, and finally to do some validation using more statistics, so more data basically. So all these next steps basically represent that we are moving to sort of data-centric approach instead of a model-centric. So previously we have basically trained the model, done some kind of error analysis, then tried to improve the model and started over. Now we're more moving into train the model, doing some error analysis, and then improving the data. So data-centric instead of model-centric. So that seems to be where we're heading next. So that brings me to the end of this presentation. I'll just give a quick summary. So the high LUMI IHC upgrade will result in greatly increased data production. We have seen that AI algorithms, especially in combination with hardware accelerators, promise to reduce the computational footprint while maintaining physics sensitivity or perhaps even improving it. I showed you MLPF, which is an R&D effort to develop a graph neural networks-based algorithm for particle flow reconstruction. And we also saw that large-scale hypertuning significantly improved this model. So although this is not yet ready for production, we think MLPF shows great promise in increasing efficiency of data processing while maintaining or potentially even improving the physics performance. So with that, I say thank you all for listening, and I'm happy to answer any questions you might have.
Yeah, thank you very much, Eric. Also, excellent presentation. The next time we could maybe invest a bit more time even, but yeah, thank you very much. Very good. I think we have already selected questions in the chat, so we maybe want to go through them from the top. And I just repeat here. I think we have a question from Pavana Kumar. Why are GNN memory intensive to train? And I think that goes to Leo.
Yes, that's the big question. I think there are two of them in the chat box. We don't really know right now. We are in the process of profiling different GNN training because looking at the theory, the adjacency matrix is never expanded fully in the data. Maybe it could be regarding the way it is parallelized on different GPUs, but I am not sure right now. I'm sorry, I cannot give an answer to this question. We are in the process of investigating it.
Okay, I think Rocco had a comment to this before we move ahead with the question. If you talk, I think we can't hear you, Rocco. Seems to be mute. Now maybe better. No, can't hear you. Okay, weird. Well, yeah, well, I think you see the message in the chat, so it maybe could be probably related to store large adjacency matrices. Do you think so, Leo, or?
I don't see the message in the chat box. I only have one referring to the RNN, I guess.
Maybe. So can you hear me now?
Yes.
Yes. Excellent. Yeah.
Okay. Yeah, I was saying that maybe it is related to the storage of the adjacency matrix, but Leo said that actually they are not fully stored, so probably it's not that. So probably my guess is wrong.
Yes, exactly. That's why I think we really need to profile what's going on under the hood with PyTorch geometrics. I see, Maurice, you asked about an analysis between PyTorch GNNs and TensorFlow GNNs. Maybe it would be the opportunity to compare how they work under the hood, both of them, when it comes to memory handling and the strategies to expand everything into tensors.
Okay, yeah, I was just out of curiosity because I see a movement more and more to PyTorch. Still, many people have TensorFlow,
yes.
And of course for RAISE, both it's kind of frameworks that matter for us. That was just a curiosity question. Then
yes, we moved from TensorFlow to PyTorch a few months ago. So PyTorch geometric was the obvious choice for us because all our frameworks were shifted at that time. We didn't compare to TensorFlow's solution.
Okay. Well, good. Thank you. Then we have GATS look like RNN in some ways. Maybe Nicolas, you want to, if you're still on the call, I'm not sure. Yeah, you're still on the call. You want to elaborate on your question, maybe?
Yeah, so it was about the graph attention networks, and more particularly on the slide that you presented. On this slide, we could see like kind of hidden state of each neuron, or we can say sorry, each
can you
node.
see the slide?
Yeah. So H1, the H1 to me means it looks like an hidden state where you have a back propagation, retroaction of itself with the alpha 1,1.
Okay.
So, and I was guessing if we didn't have with multiple layers of such inferences, if we could have catastrophic forgetting like in recurrent neural networks.
I am really not an expert into RNN and the field of recurrent neural networks, but I think what characterizes recurrency is when you stack layers that share the same weights. So basically you have a state which is updated by the same layers, by the same weights. This is not what we are doing here, meaning that the only thing which is done in parallel here is the layer is applied to each node. But then once the result is processed, we go to we pass the whole graph into another layer, maybe of the same kind, but this other layer doesn't share the same weights. So there, I don't see really the link with RNNs. Apart from that, I don't know about catastrophic forgetting, so I cannot answer differently than with a catastrophic answer.
Thank you.
I think also Rocco again had a comment maybe. Do you want to elaborate on it?
No, I mean, it was just related to the same question. And also here, my guess was that in general, from what I know, the little I know in attention models, the catastrophic forgetting is less of an issue compared to RNNs because of their intrinsic structure. So because attention models should look at the whole sequence at the same time. So so they should suffer less from these, but again, I've not used them extensively, just read some papers. So yeah, that was my comment.
Yeah, I'm like a newcomers in GNN, so thank you.
Okay, yeah, thank you very much. Good. I think then we had Pavana Kumar again. My subscription is algorithm. Do you want to maybe elaborate on it? Pavana Kumar, I hope I spell it right.
No, I think my guess is about the mutability, non-mutability of these algorithms. I mean, most of these frameworks, they force you to write code that don't mutate. So I think that blows up the memory usage because you keep stacking on your output from each of these functions. And I think that blows up the memory. There are like a lot of tricks that you can actually use to reduce this memory cost. But I don't think TensorFlow or other frameworks have really done that. That's my suspicion. It's just a guess. I'm not so sure.
Okay, any comment? Otherwise, I think Andreas has also a question.
Yes, I have a question to Leo. What I didn't fully get was how the GNNs adapt themselves according to mesh refinement or coarsening. How are they informed if coarsening or refinement is necessary, and how is then the information propagated? How is the GNN then reconstructed according to the mesh adaptation?
Okay, I didn't explain that, so that's normal. From what I presented, there is nothing that could there is no theoretical basis for this refinement or adaptation of the mesh, but you would have to build another layer, some kind of hyper optimization on top of the GNN to refine the areas where, for example, the gradients is higher, meaning that the physics is evolving more quickly or more abruptly. There is nothing in this presentation which explain it, so that's normal that you didn't get it. Just that in most papers they keep this door open, and there are heuristics to do this this adaptation. But keeping in mind that on the nodes the coordinates are stored in addition to the features. Natively the GNN is going to capture the distance to its neighbors. This is not natively encoded in a kernel, convolutional kernel, for example, where the points on the edge are a bit a square of 2 apart from the node, and it's not fully integrated in CNNs. So if inside a simulation you change the mesh, you can do that pretty easily. I have no example. I've never done it, but surely it can be done.
Yeah, I know about that, but do you think it might be possible to I mean, you certainly have some simulation data that you also input there. So maybe to at some point where you might have a change in the topology of the GNN, or let's say in the original mesh that you inform during the training the mesh on this update. Do you think that is possible?
You mean keeping the same nodes while moving them, changing the coordinates, right?
Yes, but I mean, nodes can be united, yeah, or divided. Yeah, that could be possible.
Yes.
Yeah, that depends on the change of the topology of the computational mesh or from your simulation, basically.
It reminds me a bit like this particle interactions, long and short range particles that they do in Pepsi, right? They consider for the long range interactions 4 or 5 particles as one. I think similar structure could be probably employed here when you do the adaptive mesh refinement of fire or smoke, whatever, what we had in Jülich with these principles. But I think from the learning perspective, we should be a bit careful on this. However, I think Leo is right. In the end, the latent space and then the neighborhood is captured on these nodes. So when we do the adaptive mesh refinements, we would build nodes which are automatically in the neighborhood, right, from this refined mesh.
Yeah.
And in this sense, I think it would be captured, but it requires definitely more loops to learn, because of course, from the learning perspective, I guess it needs to see that samples.
Yeah,
right? It cannot just switch like that and learn this behavior on and off, especially if you talk about coarsening again and refinement back and forth.
Yeah, I mean, when you have the progress variables that propagate through the graph through the different layers, you certainly could have something similar like you have in your computational mesh when you do the refinement, when you have strong gradients or so, where you know you should have a finer mesh. Maybe something like this could be applied here as well for the GNNs. Just an idea.
Yes, definitely. I would add that the GNNs, once it's learned, it's not directly dependent on the degrees and on the topology. So you can transfer learning quite easily by just adding some nodes with some random features or no features at all, and apply the weights that you learned on this new topology. It will transfer quite easily.
Okay. Thanks a lot for that.
Thank you.
You're muted, Morris.
Sorry, thanks for that. Sorry, I just wanted to say, I just put out here one fire simulations we have where exactly this adaptive mesh refinement is actually taking place. You see this here in the propagation of the smoke and so on. But still, as the neighborhood in the end is preserved, I think it would be not a big stretch for graph neural networks to learn that over time. But it needs some studying and I think iterative learning, because just, you know, so interactively as we see that here would be a little bit troublesome, I think, for the network representation, because you start, you know, creating nodes and collapsing them and bringing them back again. Yeah, it depends probably also a little bit on the problem you really solve with this adaptive mesh refinement and what is the frequency of the refinement.
This is true for Cartesian meshes, I think, but if you have like unstructured meshes, like tetrahedral meshes or so, then the connectivity could change. Yeah, then it's maybe not that easy anymore.
No, but I think in general it would be something like this here, right? When you see,
yeah, that's Cartesian. Yeah, yeah.
And the long range interaction here of the particles, that you would then see that you take all the 4 nodes in the neighborhood as one and learn on that. And essentially, when you break into the refinement, you would have already these learning basically then pulled on all these 4 nodes. Something like this I could see could work, but it really needs studying to do so.
Yeah.
But I see we are also already at 4 o'clock. It gets quickly. So I stopped my stuff here. But yeah, I mean, we're basically at the end of the seminar. Just maybe making another round. I think congratulations from Gail. Thank you very much also for joining, Gail. Then I maybe just close with one slide here quickly, more or less, or a couple of slides to this thanks, and give an appetizer what comes next. Can you see the slides?
Nope.
Oh. No. Okay. Just thanks everyone for joining. I don't want to take it too long. Of course, if you want to look more about RAISE, I mean, here I see most of you should know RAISE by now, so I can skip that part. And you know, we're creating the software framework where we will be in touch with many of you, also our new programmer. For Work Package 6, remember, go to the YouTube channel and subscribe. Very soon this video will be there uploaded as well. And I think just as an appetizer for April, we have already confirmed that Gabriel and his team in remote sensing, so it's a very special area that we have in RAISE, we'll talk about using quantum computing. So essentially the very specific way of using a quantum annealer, and we'll explain a little bit how we use so-called QUBOs, and here this effect of superposition essentially enables us to have a 0 and 1 computing really with a qubit at once. And for optimization machine learning, it has really good offerings. You see that a little bit here in the idea of this surface, that you essentially take water over it and find the minima instead of using, you know, stochastic gradient descent and these kind of steps. But this would be something presented next time in April based on support vector regression techniques. So I think that's all I wanted to leave you on the table. And once again, thank you very much for joining.